Hello! Coming to the end of the straight lines and coordinates chapter, sometimes called coordinate geometry here today, and therefore it makes sense that the thing we'd finish off with is by taking a look at the hardest level of question you can get asked with this particular topic area. That does therefore leave me with the usual dilemma that I have when trying to make these types of videos, which is that I first have to point out this is by no means a comprehensive guarantee of all the types of questions that you could ever get asked with this stuff, because to a certain extent that's kind of the point of the hardest level questions. They're there to test you on your ability to adapt to the brand new situation you've been faced with. You're expected to come across questions that you've never come across before and then just react with whatever you've been given to know what it is you're meant to do. And therefore, I can't tell you about those type of questions because I have not seen them yet before either. However, there's always some little gems of information I can give to you here and there based on the experience I've seen of previous exam questions, and so that's what I'm going to try to do today. So with that said, the first bit of advice I can give you is things that are generally good idea with harder questions anyway. The first of which is drawing a diagram. There are so many students that are resistant to drawing a diagram because they think it's something their teacher's just asking them to do as a chore, but actually diagrams are so useful, particularly on harder questions. That's not to say some of you might be able to do these questions that we're looking at today without drawing a diagram, but if you draw a diagram, it makes the question a lot easier, because there's certain bits of information that might be more difficult to spot when they're written down in algebra or in words, but then as soon as you can see what's going on visually, the method you need to use to approach the question suddenly becomes very clear. The other aspect to these questions is that just sometimes there is so much information going on in the question all at once that if you just try and leave it as things written on a page rather than things drawn, it again just becomes more difficult to see what's going on because the links between things are less clear until you've seen it visually. The second bit of advice I can give you, though, is also to be aware that these questions are often part of bigger multi-stage questions. For instance, these questions we're talking about today might be the part B, the part C, or the part D of a much bigger question, and therefore you should always be asking yourself when that happens in exam questions, why have they made this as an additional part to a previous question rather than just making it its own completely separate question? It's often because at least one of the previous parts to that question are going to contribute and be helpful to what we're trying to do in this last part of the question. So therefore, trying to take a look back to what you've done before, that's again where drawing the diagram comes in useful as well. It helps summarize what you've done before. It then makes it easier to spot what you need to do next. So let's start by looking at an example, and almost to hammer home the point I just made, this is a multi-step question, a multi-part question, and so therefore worth pointing out the part A and the part B actually are things we've looked at in previous stuff, so I'm actually going to whiz through those parts very quickly. It's the part C is the bit I'm interested in, but to give you an overview of the sort of experience you'd have solving this question as a whole, I'm still going to do the part A and the part B, just to show you some of the things we might have to do while we're going along through it. So to start off with the part A, which is finding the equation of a straight line. We need a point and a gradient. Good news is we've already got the point that lies on L2, and that is that point P that we've been given there. We also need a gradient. Well, we're given the information that L2 is perpendicular to L1, so that means it's got the perpendicular gradient to L1, as L1 has a gradient of 3. Therefore, that means L2 has a gradient of -1 divided by the gradient of L1, which is 3. So therefore, m is equal to -1/3 for our L2. Therefore, we've now got all the information we need to find the equation of L2. It's just y minus y1 equals mx minus x1. You know by now that if you've seen my other work on this sort of chapter, this sort of stuff, this is by far, in my opinion, the best method for finding the equation of a straight line. So therefore, whacking in the relevant information, y minus 15 equals -1/3 lots of x minus 10. We've already got the correct equation of a straight line technically. All we're doing from now on is just doing some simplifying so that it's in a easier to work with format. but also because the final answer, they often want it to be fully simplified. Interestingly, they don't ask what format they want the final answer to be in, so therefore I get to choose either y equals mx plus c or ax plus by plus c equals 0 or ax plus by equals c, whatever. I'm going to choose the ax plus by equals c style thing because if you've got fractional gradients, slightly nicer to deal with. So therefore, I'm going to start by multiplying both sides by 3 because that will eliminate the fraction that we've currently got there. So multiplying the left-hand side by 3, we've got to multiply both of those things by 3. Don't forget that. On the right, we've got the x minus 10. Multiply the brackets on the left and on the right. Gather the x onto the left-hand side so it's with the y. I'm going to choose to move the 45 onto the right. So adding 45 onto both sides, you get 55. And there you go. That's our answer to L2. On to question B. You might notice I have carried forward the answer to part A. So although we've got rid of the working to save space, we've still got the answer. So part B, well, we're told L1 and L2 intersect at the point R. We've got to find the coordinates of R. How do we find points of intersection? Well, of course, it's simultaneous equations. So therefore, it's actually very easy to do this one. We've already got that first equation in a format of y equals, which is great because it's already been turned into a ready-made substitution. So we can go right ahead and substitute it into the second equation, making sure we're writing brackets as necessary to ensure that what's meant to be multiplied by things is being multiplied by the relevant things. So multiplying that stuff out, the 3 by the 3x gets us 9x, and the 3 times by the 5, of course, gets us 15. We can gather the things together, so x plus 9x would be 10x. 55 take away 15 is 40. And therefore, that tells me that x is equal to 4. And then once I've got that x is equal to 4, y is going to equal 3 times by 4 plus 5, which is 17. So therefore, the coordinates of R, that's something worth pointing out. Don't get caught up by that. If they ask for coordinates, give your answer as coordinates. So therefore, I should write it in the format of coordinates at the end. So therefore, that's my coordinates for R. There you go, part B done. But both those questions were fairly straightforward. Heading into part C, we can see, pun not intended, that we've been given a third point called point Q. That apparently lies on L1, one of the lines we'd already been dealing with earlier, at the point where x equals minus 1, and we're tasked with finding the area of the triangle PQR. Now, what that means is the triangle has vertices at the points P, Q, and R, vertices being the posh way of saying corners. So, at first glance, actually, this is really not that bad at all, because finding areas of triangles is not exactly the most advanced maths you're ever going to come across in the world. But the reason this is a bit of a pain is just because some students might go about this question in a much more long-winded fashion than they really need to, because they're unaware of the hints that have already been given earlier in the question. The way that makes it easier to spot those hints, though, is by drawing a diagram to summarize the information that we've been already doing in those previous parts. So we could start by drawing the fact we've been dealing with L1 earlier in the question. So that's going to be a relatively steep line, arguably more steep than what I've shown there, but that'll do. It's got a y-intercept of 5, of course. X-intercept, you could work that out. It's minus 5/3 in case you're interested, but it's not going to affect many things in this question. And then we've got a second line, L2, which is perpendicular to this line, but goes through the coordinates 10, 15. So if we say 10, 15 is, I don't know, let's say it's over there, then L2 is a line that's perpendicular to L1. Horrendous drawing of a line. It doesn't matter. See, here's the part of the point I'm making. You're not getting marked on this diagram. It's purely for your own benefit. So the fact this diagram is dreadful, it doesn't matter. I'm chill about it. Now, interestingly, we had already pointed out earlier as well that where these two lines intersect is also point R. And then we've also got this new point, point Q, which lies on L1. Now, this is where it might have been helpful to also have labelled my two lines. So the fact that this was L1 and this over here was L2. So we've got this other point, Q, which is where x equals minus 1. So that might be somewhere around here. That's called point Q. And we should work out the y coordinate. That would probably be useful. So plugging in x equals minus 1 into our equation of our line, we're going to end up with y is equal to minus 3 plus 5, which is 2. So that's the coordinates minus 1, positive 2. Now, the reason doing all that was so useful is it's now actually very clear that this really is a very easy question indeed, because we're trying to work out the area of a right-angled triangle. And so therefore, the easiest way of finding its area would be to treat, let's say, this side here as the base, and then this side here, Q to R, as the height. Because if you do that, it's just going to be the classic half base times by height. Well, easy. So obviously, drawing that is important. Also, the reason it's important to draw this stuff is because you might be very quick to spot this was a right angle triangle just because of the fact it mentioned L2 and L1 were perpendicular in the words. But it's important to still draw the diagram because you can see which letters more clearly are the ones that will form the sides that are perpendicular, which is important for when you're trying to find the base and the height. And so, calculating the distance from R to P. That, of course, will be calculated using distance between 2 points, a method we looked at earlier in this chapter. So that will be the change in y coordinates squared plus the change in the x coordinates all squared. So therefore that would be 4 take away 10. Because it's squared, it doesn't matter that that's a negative number inside. Remember, of course, this formula is basically Pythagoras. So we've got 2 squared plus minus 6 all squared technically there. So I've just got to work that out. Is that going to come a nice number? No, it's root 40. Is that a problem? No, not really. We'll leave it as a surd. That could arguably be rewritten as 2 root 10 if you like. But there you go. We then could also work out the length from Q to R, because that is also going to be our other important length for the triangle. So therefore the difference between the x coordinates all squared, so therefore it's Q and R we're interested in this time, so that's minus 1 to 4. So that's let's do it easier if we do 4 minus minus 1 all squared plus the difference between the y coordinates. That's why we had to work out that y coordinate earlier. So 17 take away 2 all squared. We've got to work that out as well. Is that very nice? No. That would be, what would it be? 225 plus 25, which is square root of 250, which is 5 root 10. There you go. So therefore the area of the triangle is going to equal half times 2 root 10 times by 5 root 10. Which could be done by hand because it's actually nice surds, but if you were struggling with that, you could just type it onto the calculator, not a problem. But for your interest, it's going to be 5 times by root 10 times by root 10, which is just 5 times by 10, which is just 50. So there you go, that's the answer to the question. The calculations for this were not very difficult to do at all, and it's really important therefore to point out that it's just about being aware that what you've done in the previous parts are helpful, but then also drawing that diagram made it really clear what was going on. So I knew what I had to do with what thing to get what I wanted. So there we go. That's my advice put into action. However, some added notes, which is that it's worth pointing out. Sometimes you're asked to work out areas of triangles, but they're not always going to be these nice, convenient right-angled triangles. So, of course, there are methods for dealing with that as well, particularly in the chapter of trigonometry, but the problem is if you're not given an angle, that's still not going to be nice. So there is another type of thing they can ask where it'll be not a right angle triangle, but still quite easy to work out the triangle just because of the type of triangle they're giving you. What you're looking out for are triangles where one side of the triangle is parallel to either the x-axis or the y-axis. Because in that case, to work out the area of the triangle, you've just got to use half base times by height, because all you've got to do is use the side that's parallel to one of the axes as the base, and then it's not going to be too bad to work out the height then in relation to that. But how? Well, let me show you an example. We're trying to work out the area of a triangle with these coordinates. Would you just be asked this as a question by itself? No, it'll be a part C to something. Maybe you have to do some effort to find some of these coordinates first in some of the earlier parts of the question. It'll be more involved than this, but I'm just trying to show you a little trick that, you've got to be aware of in some cases. So we're trying to find the area of the triangle with these corners. So step 1, draw a diagram. It's a lot easier to see what's going on if you do that. So we've got 2, 1. Let's say that's roughly there. I don't need to draw accurately. It's just about seeing where stuff is in relation to the other things we've been given. We've been given another point, 9, 10. That will be further to the right and further up. Let's say it's over there. And then lastly, we've been given 213. That's important because it's going to have the same x-coordinate as the other coordinate we'd already shown, but a higher y-coordinate than either of the other two coordinates we'd shown. So that's why I know it's there where I've drawn it in relation to the other two we'd already drawn. So the triangle looks something like this. Now the reason that's interesting, because immediately, oh my goodness, just like what we were just talking about, this is a triangle where one of the sides is parallel to one of the axes. In this case, we've got this side up here that's parallel to the y-axis. That's important because it means we can treat that at the base, and therefore it's actually going to be very easy to work out the length of the base and the length of the height, because the length of the base can just be found by comparing the y-coordinates of the two coordinates that form the base, because that's the only bit that's changing. Because they've got the same x-coordinate, 2, 1 and 2, 13, it's only the y-coordinates that are affecting the distance between those 2 points. So therefore you instantly know that's a length of 12 in between those 2 points. We've got the length of the base. And then to work out the length of the height, well, because the entire base has the same x-coordinate, it's therefore the x-coordinates that will help you work out the height, because you've got to look at the difference between the x-coordinates of the entire base, which is 2, and the x-coordinate of the very top of the triangle, which is 9. That's important because it means 9 take away 2, in other words 7, is the height of that triangle. So therefore working out the area of this triangle is super easy. It's just half times 12 times 7, which is easy because that just means our answer is 42, and therefore you're done. So therefore that's something to watch out for, looking out for situations where the base of the triangle is either parallel to the y-axis or parallel to the x-axis, because you're then just having to use individual just the x-coordinates or individually just the y-coordinates to find either the base or the height. So there you go, that's some general advice for dealing with some certain scenarios. It seemed like we were just finding triangles in this video. That's just because that's a common thing they've asked for in the past, but they could ask for more varied things than this. But that's some general advice I wanted to give you specifically for today. Hopefully you find that useful. I'll see you in a future video. Goodbye.